Hello. In this video, we're going to discuss energy and the work-energy theorem. We start by defining what energy is. Energy is the ability to do work. That's the definition of energy. We are primarily interested in forms of mechanical energy for the purposes of this video, even though there are many other types of energy. But today, we're going to only discuss forms of mechanical energy. The first form of mechanical energy that I would like to discuss is kinetic energy. Kinetic energy is the energy that an object has because of its motion. The formula for kinetic energy, by the way, the variable for kinetic energy is just Ke, the first two letters of the words kinetic and energy, and that equals 1/2 mass times the velocity squared. So the faster an object moves, the greater its kinetic energy. Now, as you can see, kinetic energy can never be negative because neither mass nor velocity can be negative. Now, how can we show that objects with kinetic energy can do work? In order to do this, we are going to try a little demo here. So what I have here is a toy car, which is going to come over. The toy car now hits the rock, and the rock moves. So the toy car exerted a force on the rock, and the rock moved, which means that the toy car, because it had a velocity and kinetic energy, was able to do work on the rock and move it. So this is a demonstration that objects with kinetic energy can do work. The next topic I'd like to discuss is conservative forces and potential energy. Now you may ask, what are conservative forces? Well, there are many different ways in which one can classify forces, and one of the ways we learned when we did Newton's laws of motion, we said that there were two types of forces. There were field forces, which act at a distance, and there were contact forces, where you need contact in order for the force to act. There are other ways of classifying forces too, and we're going to see one of those other ways now. So we're going to classify forces again, but this time we're going to classify forces into two types: non-conservative forces and conservative forces. Now, conservative forces and conservative forces, does this mean that, conservative forces are really old-fashioned and non-conservative forces are really hip? Not so much. Essentially, conservative and non-conservative are the names given to forces because of the way they affect the energy of an object. Conservative forces, when they do work, the work done by a conservative force does not depend on the path. It just depends on the starting and ending positions. Conservative forces, when they do work, they do not change the total energy of an object. Non-conservative forces, on the other hand, when they do work, the work done by the non-conservative forces is path-dependent. Examples of non-conservative forces are friction, tension, applied forces, and normal forces. When these forces do work, they do change the total energy of an object. Now let us look at the work done by some types of conservative forces. We're first going to consider the work done by gravity, and we're going to see how that impacts energy. Now, gravity is a conservative force, but we don't have to take my word for it. Let us see whether indeed that is the case. So I have an object here, a painted little piece of wood, and I want to take it from its current position to a new position. As I said, we want to take this painted block to a new position. So we start the painted block and we move it to this new position. So what are the forces that are acting on this block? Well, ignoring air resistance, the only force acting on this block is Fg. So what is the work done? Actually, other forces could be acting on this block, but especially since I was the person who moved the block, so yes, my force is acting on it. But we are interested in the work that's going to be done by Fg. So we draw the force Fg, and then we determine the work that is done by Fg. So let us say that delta x is the distance or the displacement that we've given the rock, or block actually, and the work done then would be, using the formula for work, the work done by gravity would be the force of gravity times delta x, the displacement, times the cosine of the angle between the direction of the displacement and the direction of Fg. Now, as you can see, we have a 90-degree angle there and an angle theta. So, taken together, this angle is 90 degrees plus theta. So therefore we write Fg times delta x times cosine 90 plus theta. Now from trig, cosine 90 plus theta is actually negative sine theta. So we substitute that. So the work done by gravity becomes negative Fg times delta x times sine theta. But delta x sine theta, if you look at the triangle up there, is just the length of the green arrow right here. Let us say that the height of that arrow is h. Therefore, we can substitute h for delta x sine theta, and we get that the work done by gravity is negative of Fg times h. Now, in order for gravity to be a conservative force, we ought to be able to get from the point where we started to the point where we ended up, taking a different path, and the work done by gravity should stay the same. Let us see if that indeed does happen. So this time what we're going to do is we're going to first move the block up and then over. And now I'm going to return the block to where I started because I want to draw the free body diagram for this block. So again, we're considering the work that's done by gravity. So I draw the force of gravity acting on the block, and I consider the work done by gravity during each of the two displacements. Now the vertical displacement that I gave this block, which is represented by the orange arrow, is h, the same height as it was before. And the angle in this case is 180 degrees. For the second displacement, the angle is 90 degrees between the direction of the force of gravity and the direction of the displacement. Now, what we're going to do is we're going to look at the work done by gravity during each of these two displacements. And when we add those two together, we get the total work done by gravity as the block moved from its starting position to the same ending position that it had before. So the work done by gravity for the first displacement would be Fg times h times cosine 180. And the work done for the second displacement, where the displacement is delta x, would be Fg times delta x times cosine 90, because that's the angle between the two. However, cosine 90 is 0. Therefore, the work done by gravity again becomes negative Fg times h, which is the same as what we had for the previous displacement from the beginning, from the starting point to the ending point, where we went straight from the starting point to the ending point. So the same as before. We're going to do the same thing again. However, this time we're going to do an even more complicated motion. So I'm first drawing the arrows, the displacements. So we're going to do 4 displacements to get from the starting position to the ending position that we have. So we first go up a distance h1, then we go to the right, a displacement delta x1, and then we go down a displacement h2, then we go right, a displacement delta x2. Now I bring the block back and I'm going to draw the force of gravity, and we're going to figure out the work done by the force of gravity in order to take the block from the starting to the ending point following this route. So h1 was the first displacement, delta x1 was the first horizontal displacement, h2 was the downward displacement, and delta x2 is the second horizontal displacement. We draw the force of gravity. Now, the force of gravity, the work done by gravity will be the sum of the work done by the gravitational force as the block goes through each of the 4 displacements, all of them summed up together. Now this angle is 180 degrees. So the work done by gravity is going to be Fg times h1 times cos 180 degrees plus Fg times delta x1 times cos 90 degrees plus Fg times h2 times cos 0 degrees, because for the downward displacement, Fg and h2 have the same direction, plus Fg times delta x2 times cosine 90. Now cosine 90 happens to be 0, so we see that for the two horizontal displacements, delta x1 and delta x2, gravity does no work. So we're left with the work done by the force of gravity during the two vertical displacements. So gravity does negative work as the block is pulled up through a displacement h1 vertically, and then the force of gravity does positive work when the block is pulled down vertically h2. So when we put these two together, we get Wg equals negative FgH1 plus FgH2. Now this is negative Fg times H1 minus H2. But H1 minus H2, we see, is just H. Therefore, the work done by gravity is negative FgH, just the same way as it was before. So the work done by gravity does not depend on the path. The work depends only on the starting and ending points. Gravity is therefore a conservative force. Now let's check what happens with non-conservative forces. I'm going to look at the work done by friction, which is one of our most familiar non-conservative forces. So we've got another painted block, and this painted block is going to be displaced to the right, and there's a force of friction acting on it, which is opposite the direction of its motion. And we can see that the angle between the direction of the displacement, the green arrow, and the force of friction is 180 degrees. Now we're going to say that delta x is equal to capital D. And so the work done by friction is going to be the force of friction times D times cosine 180 degrees, which is just negative the force of friction times D. Next, let's try a different route. Again, the same block, and we're going to end up in the same position. However, we're going to take a longer route to go there. So we're first going to have a displacement downwards of D1. Then we're going to have the force of friction in this case is acting opposite the direction of the displacement, which in this case is up. Then we're going to have a diagonal displacement, D2, and the force of friction acts opposite the displacement, because that's what the force of friction does. And the block is going to end up in the same position that it was at the end of the last displacement that we discussed. Now this time, the work done by friction is going to be the work done by friction during each of the two displacements added together. Now in each case, the angle between the force of friction and the displacement is 180 degrees. So now let's calculate the work done by friction on the second trip. The work done by friction equals the force of friction times D1 times cosine 180 degrees plus FF, the force of friction, times D2 times cosine 180 degrees. So we get negative the force of friction times D1 minus the force of friction times D2, or negative the force of friction times D1 plus D2. Now as you can see, D1 plus D2 is definitely bigger than D. So friction did more negative work on the second trip than it did on the first. So the work done by friction on the first trip was negative the force of friction times d, which is definitely not equal to the negative force of friction d1 plus d2, which is the work that friction did on the second trip. So what does this mean? The work done by friction in moving from one point to another does depend on the path taken. So friction is a non-conservative force. So the exercise that we followed is actually pretty illustrative of how we discuss conservative and non-conservative forces and the way they behave. We're going to resume our discussion by talking about conservative forces and another form of mechanical energy called potential energy. The work done by conservative forces, as we saw, depends only on the starting and ending positions. The work done by conservative forces can actually be thought of as a change in energy, a kind of energy that depends only on the position or configuration of an object. So this kind of energy is called potential energy, and it depends only on the position of the object or the configuration of the object. The position of the object, typically gravitational forces when you're in different places, at different heights, you have different amounts of gravitational potential energy, or configuration when you think of a spring. If a spring is stretched or compressed, it has potential energy. The potential energy, the variable that we use for it is PE. Now we can define WC, where the subscript C represents conservative, and we'll replace C by G when we're talking about the work done by gravity. We would replace the C by S if we're talking about the work done by a spring. And, later on in the year, we will learn about the work done by electric fields. And when it's work done by an electric field, it'll be W with a subscript E. Gravitation, spring forces, or elastic forces, as you could call them too, and electrical forces are all conservative forces. It turns out that we can define that the work done by a conservative force is equal to the negative of the change in potential energy associated with that conservative force. So the work done by the gravitational force would equal the negative of the change in the potential energy, gravitational potential energy. The work done by a spring would equal the negative of the change in spring potential energy, and so forth. Now, let's look at gravity. Let's say that we have a ball that is located at a height h1 above the ground. And then let's say that we bring it to a new position. So let's call that position A. And let's say we bring it to a new position, position B, which is at a height h2 above the ground. Now, what is the work that gravity does as this ball is moved from position A to position B? So we draw the force of gravity, and we draw the delta y displacement in the vertical direction. And this delta y makes an angle of 180 degrees with the direction of Fg. So the work done by the force of gravity would be Fg, the force of gravity, times delta y, times cosine 180 degrees, which is the angle between the direction of Fg and the direction of delta y. So this implies that the work done by gravity, since cosine 180 is just negative 1, is just Fg times delta y, negative. So since Fg is just mass times the acceleration due to gravity, so it'll just be negative mg delta y. Now we can see that delta y is just the difference in the heights, h2 minus h1. So we can rewrite Wg as negative mg h2 minus h1. So that means, from our previous definition where we said that the work done by a conservative force equals the negative of the change in potential energy associated with that conservative force, so we can use that to say that the change in gravitational potential energy when you move the ball from point A to point B is equal to positive mg h2 minus h1. Now, if h1 was 0, we are allowed to choose h1 equal to 0 because we can say that that is our reference level. We are choosing to make it 0. And we are allowed to do that with gravitational forces. Then the potential energy of position B relative to position A is just PE gravitational equals mgh, where h equals h2 minus h1, the difference in the two heights. So this is how we define potential energy. Gravitational potential energy. So this gravitational potential energy is interesting. We have freedom to choose our reference level where we're going to make the gravitational potential energy 0 anywhere. So if you happen to be below the point where the reference level is 0, then your gravitational potential energy will be negative. If you choose the reference level below you, then your gravitational potential energy relative to that reference level will be positive. So gravitational potential energy can be negative or positive. It all depends on where the reference level h equals 0 is considered to be, and we have a choice in how we do that. Often we will choose the lowest point in our problems to be h equals 0. That makes a lot of sense usually. Okay, now let's look at a different kind of conservative force and the potential energy associated with it. So now we're going to look at elastic or spring potential energy. So here's a spring, and there's the same spring but stretched out. And let us say that the spring has been stretched out by an amount x from its equilibrium position or unstretched position. So the x that we call x is usually called the extension or compression of the spring. Now, anytime a spring's length is changed from its undisturbed length, then the spring tries to get back to its undisturbed length. And the farther you extend the spring or compress the spring, the stronger this force is. It turns out that the spring force is negative k times x, where the k is the spring constant and x is the extension. Now, what does a spring constant mean? Well, the stronger the spring or the stiffer the spring, the more it will pull back when it is deformed. Deformed as in either extended or compressed. So strong springs will need a stronger force to pull them out. Now, as you can see, this force is a variable force. So as x changes, the spring force changes. So it is not possible in this case to directly apply the formula work equals force times displacement times cosine of the angle. So what are our options? What we do is we draw a graph of the force, and the area between the graph and the x-axis is going to be the work done by the force. So we draw a spring force versus spring extension graph. Now, as you can see, this graph should be a straight line with a slope of k. There we go. And so the force, as you can see, increases as the extension increases. So the coordinates of the point at the end of the graph are x, which is the extension of the spring, and negative kx, which is the spring force, when the spring has been extended by an amount x. So now, in order to find the work, we find the area of the triangle below the x-axis. Now, because this is below the x-axis, this area is going to be negative. So the work done by the spring is going to be 1/2 the base times the height of the triangle, which is going to be negative 1/2 x times kx. So negative 1/2 kx squared. But a spring force is a conservative force. So therefore, the change in potential energy of the spring, or the potential energy stored in the spring as a result of extending or compressing the spring, is going to be given by the potential energy change equals negative of the work done by the spring. So the change in potential energy of the spring is 1/2 kx squared. Or in other words, if a spring is extended by an amount x, then, or actually compressed or extended by an amount x, then the spring potential energy will be 1/2 kx squared. So this is the amount of potential energy stored in a spring. Now, do objects with potential energy have the ability to do work? Remember, we said that energy was the ability to do work. Well, think about it. If you pressed a block against a spring and compressed it, then the spring would have some potential energy stored in it. If you were to release the spring, then wouldn't that spring release its potential energy and do work on the block as it stretches out? So the potential energy stored in the spring is capable of doing work. So it is indeed a form of energy. Next, we're going to talk about the work-energy theorem. Here, we're going to relate work to energy. Since energy is the ability to do work, therefore work and energy must be interrelated. Indeed, work and energy are both measured in joules, and work and energy can be converted from one to the other. So, we're going to begin with a discussion of Newton's laws. You might remember from Newton's laws, when a net force acts on an object, the object will accelerate. This acceleration can either cause a change in magnitude and or the direction of the velocity. If the net force does work, then it changes the velocity, changes the magnitude of the velocity and the kinetic energy of the object. Because you might remember, the kinetic energy is 1/2 mv squared, which means that if v changes, then, or rather the magnitude of v changes, then the kinetic energy must change too. So the work done by the net force changes the kinetic energy. So the work done by the net force equals the change in kinetic energy, or kinetic energy final minus kinetic energy initial. Now, in most situations, you'll have both conservative and non-conservative forces acting on an object. So when I talk about the net work, I can actually say that the net work is the sum of the work done by conservative forces and by non-conservative forces. So WNC is the variable that I use to indicate the work done by non-conservative forces, and WC, as before, is the work done by conservative forces. So the sum WNC plus WC is equal to W net, which in turn is equal to the change in kinetic energy. But we know that the work done by conservative forces is just equal to the negative of the change in potential energy. So that work, WC, must equal the negative of the potential energy final minus the potential energy initial. Substituting that into the previous equation, we get WNC, the work done by the non-conservative forces, minus the final potential energy plus the initial potential energy equals the final potential energy minus the initial potential energy. Oops, I have the wrong sign there. Let's fix that. I think that might be a little too big. So I fixed that sign. So kinetic energy final minus kinetic energy initial. Now this can be rearranged, and we can see that kinetic energy initial plus potential energy initial plus the work done by the non-conservative forces equals kinetic energy final plus potential energy final. Now the sum of kinetic energy final and potential energy final is called the mechanical energy final. And the sum of the kinetic energy initial and potential energy initial is the mechanical energy initial. Mechanical energy is the sum of kinetic and potential energies. So what this equation tells us is that if a non-conservative force does work, then it changes the mechanical energy of an object or a system of objects. So the sum of the kinetic and potential energies initially is modified by the work done by the non-conservative force, and you have a new kinetic energy final and potential energy final. So if the non-conservative force does negative work, as would happen in the case of friction or air resistance, then the mechanical energy of the object would decrease after the work done by the non-conservative force. However, if the non-conservative force can do positive work, as in the case of applied force, though applied forces can do negative work too, in the case of applied forces, if the applied forces do positive work, then the work done by the non-conservative force will increase the mechanical energy of the object. So the moral of the story is that anytime non-conservative forces do work, they cause a change in the mechanical energy of an object. Now this is called the work energy theorem. Now what happens if there is no work done by non-conservative forces? Then what we get is what is called the law of conservation of mechanical energy. Now, the work energy theorem states that the kinetic energy plus potential energy, or mechanical energy initially, when added to the work done by the non-conservative force, gives you the final mechanical energy. Now, if no work is done by the non-conservative force, then what do we have? We have the sum of the kinetic and potential energies, or the mechanical energy initial, is equal to the mechanical energy final. Mind you, this is not saying that the kinetic energy does not change or the potential energy does not change. All we're saying when we say this is that the sum of the kinetic and potential energies does not change. So it's quite possible that the kinetic energy will increase, but any time the kinetic energy increases and there is no work done by non-conservative forces, it must mean that the potential energy decreases, so that the change in kinetic energy is balanced by an opposite change in potential energy. So the changes balance each other so that the sum stays constant. Now, this is called the law of conservation of mechanical energy, as I mentioned below, and it is one of the most important laws for solving problems. Now, here's a note. There could be multiple forms of potential energy in a scenario. So it is not necessarily true that we'll have only one kind of potential energy. So when I say kinetic energy initial plus potential energy initial, the potential energy initial could be more than one term. It could be gravitational potential energy and spring potential energy, and later on, electrical potential energy. So the PEI that I have there and the PEF that I have there could be the sum of multiple types of potential energy. Now let's do some examples where we apply the work energy theorem. The first example that I'm going to do is something that you guys are very, very familiar with. So NRG tosses up a ball with a velocity of 6 meters per second. How high does the ball rise? Disregard air resistance. So here's a ball, and we have both the starting position and the ending position. So the ball starts out low and goes high. Now we always begin these problems with a free body diagram because, as you guys may have noticed, forces do work. So let's draw the force of gravity. The next question is, are there any non-conservative forces? No. So if there are no non-conservative forces, since we're ignoring air resistance, that means that WNC, the work done by the non-conservative forces, must be 0. Now that is awesome, because what that means is that the law of conservation of mechanical energy applies. Or in other words, the sum of the kinetic and potential energies to begin with equals the sum of the kinetic and potential energies after the ball rises. Next, we're going to write our givens on the diagram. You'll see that I do this a lot for problems on energy, because as it turns out, labeling things on the diagram works much better. It's visually more helpful. So, to begin with, the initial velocity is 6 meters per second, because energy, that's the velocity with which she tossed the ball up. Now, each initial is 0. Now, each initial may not actually have been 0, but I'm allowed to choose whatever level I want to be my 0 level for height. So I do the most logical thing, and I choose the lowest point to have a height of 0. Now, the reason why I do this is that it makes life a lot simpler. It turns out that I don't have to do a lot of subtracting and all of that when I choose my lowest level to be 0. Now at the top, V final is 0, because remember, at the top of its path, the velocity of the ball when it's in free fall is 0. That's what happens at the max height. And we want to find H final. Now we're going to apply the work energy theorem to this problem. I find that it is useful to organize my problem in a table. So I'm going to make 3 columns to this table. The first column is going to have information for the work done by the non-conservative force. The second column, and in this particular problem, because there are no non-conservative forces, there is no non-conservative work. The second column has information for the initial mechanical energy. So here's where I list and calculate the initial kinetic and potential energies. And the third column is the final mechanical energy. Here's where I'll calculate the final kinetic and final potential energies. So let's begin with the initial kinetic energy. You're not given the mass, but usually that's not a problem because we just leave mass in there and eventually the mass is going to cancel out. So I substitute 6 for the initial velocity from the givens, and I find that the initial kinetic energy is 18 times m. Next, let's look at the potential energy. Now, in this case, there are no springs, so the only type of potential energy you're going to have is the gravitational potential energy. So the initial gravitational potential energy is just the mass times the acceleration due to gravity times the height. And so it's just m times 9.8. And since the initial height is 0, that's just 0 joules. Now let's turn to the final mechanical energy. The mechanical energy that the ball has at the top of its motion. So the final kinetic energy is 1/2 mv final squared. Now at the top of the motion, as we said before, the final velocity is 0. So the final kinetic energy is also 0. And the final potential energy, this time the height is not 0. So it's mgh final, and that is equal to 9.8 times m times h final. So now we've got all the parts of the work energy theorem, and we can now substitute into the work energy theorem to do the problem. So the work energy theorem states that WNC plus kinetic energy initial plus potential energy gravitational initial plus kinetic energy final plus gravitational potential energy final. Oops, I said that incorrectly. The sum of the non-conservative force and the initial mechanical energy equals the sum of the kinetic energy final and gravitational potential energy final. So from our chart, we fill in what we have. So 0 plus 18m for the initial kinetic energy plus 0 for the initial gravitational potential energy equals 0 for the final kinetic energy plus 9.8 mh final for the final gravitational potential energy. Now cleaning it all up, we get 18m equals 9.8 mh final. As predicted, the masses cancel out. And doing a little bit of algebra, we find that h final equals 1.84 meters. So the ball rises to a maximum height of 1.84 meters. Now you guys might remember, we did the same problem using kinematics, did we not? So why bother doing it with energy? Well, it's a new way of doing the problem, and for this particular unit, I will expect you to use energy techniques to solve problems that could otherwise have been solved using Newton's laws or kinematics. Let's do another example. Now, before I go there, there's a note that I want to make. If we had considered air resistance, then the work done by the non-conservative force would not be zero. Here's a question for you. Would the ball have risen as high or to the same height? So here's our second example. Forgive my voice. I have a little bit of a throat problem right now. Now, box goes to the right. Starting with a velocity of 8 kilometers per hour and then slows down to a stop after traveling a distance of 3 meters. Determine the coefficient of kinetic friction. So obviously, if the box is coasting to a stop, there must be something stopping the box, which means that there must be kinetic friction. So as before, we draw a picture and then we follow it up with a free body diagram. Because remember, forces do work. So when we're looking at problems, we really want to know what the forces are doing in the problem. So we have the usual forces. We have the force of gravity. Then we have the normal force. And then we have the force of friction. Now notice that we do not know the mass of the box. This is similar to the previous problem where we did not know the mass of the ball. Now, we can still write that Fg equals mg equals 9.8 m. We can still do that even though we don't know m. We just hope that mass is going to cancel out somewhere along the way. Now, the box is moving horizontally, which means that there is no acceleration in the vertical direction. So that means that the sum of the vertical forces is 0. So the normal force must equal the force of gravity, which must equal 9.8 m. So let's substitute that in there. Now, let us label our givens on the diagram, as I did in the previous example. Oh, but before we do that, are there any non-conservative forces? Yes, an emphatic yes, because there are 2 non-conservative forces. The normal force and the force of friction are non-conservative. Next, we'll write the givens for determining the energies right on the diagram because it's helpful to do that. So, to begin with, the box had a velocity of 8 kilometers per hour, which, when we convert to meters per second, becomes 2.22 meters per second. And because the box is moving on level ground, therefore, I can choose the initial height to be 0. And, in fact, the final height will also be 0 because the box doesn't move up or down. It's basically moving horizontally. Now we're going to organize the problem by making a table. Oh, the final velocity is 0 because we said that the box coasts to a stop. And the final height, as I mentioned before, is also going to be 0. Again, I make the same chart that I did for the first example. The first column is WNC. The second column, WNC, and that's where we're going to be listing the work done by the non-conservative forces. And then the second column is the column for the information about the initial mechanical energy. And the third column is the column with the information about the final mechanical energy. So let us draw Fn, which is our first non-conservative force. And let us draw the displacement, which is 3 meters. To the right. Notice that the angle between the normal force and the displacement is 90 degrees. So we can write that the work done by the normal force is the normal force times delta x times cosine 90. And since cosine 90 is 0, therefore the normal force does 0 work or no work. Next, let's look at the force of friction. The force of friction is acting to the left, the displacement is to the right. The angle between the direction of the force and the direction of the displacement is 180 degrees. So the work done by friction is the friction times the displacement times cosine 180 degrees. So that would just be negative 3 times the force of friction. So the work done by friction is the force of friction times the displacement, which is 3 meters, times cosine 180 degrees. So that becomes work done by friction equals negative 3 times the force of friction. Now the total non-conservative work is the sum of the non-conservative work done by both normal force and the force of friction, which in this case is just the work done by the force of friction. So the work done by the non-conservative force is just negative 3 times the force of friction. Next, just as we did in the previous example, we fill out the information for the initial mechanical energy. We begin with kinetic energy, which is 1/2 mv initial squared. So we don't know mass, so we leave m the way it is, and we substitute 2.22, which is the initial velocity for v initial. And doing the math, we get the kinetic energy initial equals 2.46 times m. We next do the potential energy, the gravitational potential this time. There are no springs in this problem, so there is no spring potential energy. So the gravitational potential energy equals the mass times the acceleration due to gravity times the initial height, which the initial height is 0. So initial gravitational potential energy is 0. Next, we do the final mechanical energy. So we repeat the same process. We do the kinetic energy first, and we substitute final kinetic energy equals 1/2 m times v final squared. We substitute 0 for v final, so the final kinetic energy is actually 0 joules. The final potential energy, the object is still at the same height that it was before, so there has been no change in the potential energy, the gravitational potential energy. It still continues to be 0. Now we're ready to apply the work energy theorem. Here's a statement of the work energy theorem. The non-conservative work plus the initial kinetic energy plus the initial potential energy, gravitational this time, equals the final kinetic energy plus the final gravitational potential energy. So we have negative 3 times the force of friction, which is the non-conservative work, plus 2.46 m, which is the initial kinetic energy, plus 0. All of this information, I'm just getting it from the chart, and that equals 0 plus 0, which are the final kinetic energy and the final gravitational potential energy. Doing the algebra, we find that the force of friction equals 0.82 m. Now, we know that the force of friction is given by the coefficient of friction times the normal force. So we substitute that for the force of friction. Next, we put in, or rather substitute, 9.8 m for the normal force. We found that in the beginning of the problem. Again, conveniently, we see that the mass does indeed cancel out. And so we get that the coefficient of friction is 0.82 divided by 9.8, and that equals 0.084. So mu k, the coefficient of friction, is 0.084. So this is how, ladies and gentlemen, you use energy concepts to solve problems. It may seem to you that there are a lot of steps involved, and it may seem to you that we can do these problems using Newton's laws and so forth, but we will soon encounter problems where it is not easy to apply Newton's laws or kinematics to do the problem. And in these cases, energy is an incredibly powerful tool, and the work energy theorem is an incredibly powerful theorem that we can use to solve some pretty complicated problems. Okay, have fun. Bye.